Okay, everyone. What I'm going to be doing now is continuing with where I left off, finishing the equilibrium section, and then talking about acids and bases in equilibrium to help you understand next week's lab as well as moving forward. So basically, if you have any questions, just email me or come see me in my office, and I'll be glad to go over anything with you. What I'm going to do now is open up the PowerPoint to start, and we'll get things going. Okay, I'm going to have some overlap here and continue where these things are. So now I'll go back to the share the screen with you now, and we'll continue where we're left off. This repeats a little what was done before. Okay, what I'm going to do now is summarize equilibrium constants, what we already addressed in the earlier lab, and essentially continue here. And at equilibrium, the rates of the forward and reverse reactions are equal, and the concentrations of the reactants and the products are constant. So essentially, if you've got A plus B goes to CC plus D, it goes in both directions, and you get the KEQ there from that. And you have the constants of each, the concentration of C to the C power times the concentration of D to the D power, to the D power over the concentration of A to the A power and the concentration of B to the B power. That's essentially what's going on with this. And it's a value representing the unchanging concentrations and the products in a chemical reaction in equilibrium. So for the general reaction at a given temperature, you get a structure that looks like this, and where you have the products over the reactants there. For the reaction here with ammonia, that would be essentially this equation here. And then for this reaction, you get this equation. The magnitude of the equilibrium constant indicates the extent at which the forward and the reverse reaction take place. So essentially what you have is a combination of factors where you have that if you add hydrogen to that side, it'll shift to the right. And so in this case, the KEQ is 425 degrees, at 425 degrees Celsius is 54.8. And that magnitude indicates that it goes to the right, and that essentially is the driving force for the reaction to take place. At equilibrium, more product than reactant exists in this point. For this one, at 400 degrees Celsius, you've got more reactants present, it goes to the left. And so then you have a number much less than 1. More reactant than product exists. When the molar concentrations of all species are known, the KEQ can be calculated by substituting the concentrations into the equilibrium constant expression. So calculate the KEQ for the following reactions, and basically you set up that formula, you plug the values in, you get 31, and then there's some more product constants that is important to understand. Water ionizes to a slight degree. Essentially, you can look at it this way also. H2O goes to this, and then H plus OH minus for some consistency. And then this is a liquid. And so basically the KEQ would equal the concentration of H plus times the concentration OH minus divided by the concentration of water, which is essentially 1 liquid water. So you get a KW here, which is equal to H plus times OH minus. And that KW at 25 degrees Celsius equals 1 times 10 to the minus 14. So more simply like this, at equilibrium, the hydrogen ion concentration equals the hydroxide ion concentration 1 times 10 to the minus 7. The water equilibrium constant is called the ion product constant for water. And that's what's involved regarding there, because essentially if you have the negative log of the hydrogen ion concentration, which is defined as the pH, you plug this value in here and you get a pH of equals 7. That is officially neutral for just water. Okay. And then you have the KW like that, 1 times 10 to the 14. What is the concentration of hydrogen ion and OH in a 0.001 molar solution? And this is related to what we did this week in lab. HCl is 100% ionized. So you plug the values in there. The hydrogen ion concentration is 1 times 10 to the minus 3. You solve it for OH. OH is equal to this. And you have 1 times 10 to the minus 11. And in this case, the pH is going to be equal to the negative log of that. Okay, and so the pH will be equal to 3. In this case, the pH is equal to 11. The 11 there, and then the 3. Okay, so that's where the pH comes from in these kinds of formulas. So what is the pH of a 0.01 molar sodium hydroxide solution? Sodium hydroxide is 100% ionized. You plug the values in, you solve it for the H plus concentration, plug the values in there, and you get the 1 times 10 to the minus 12 there, and this pH is going to be 12 in this case. The pH is equal to 12 in this case, okay? The pH can also be calculated by calculating the pOH first, and you plug that in there and then subtract it from water. And so basically in pure water, this is 7 plus 7 equals 14. So basically you can rearrange that and get the pH, and that equals there. And then you have pH and pOH like that listed for acids, neutral, and base. Now, there are various other ionization constants, which are important to keep in mind too. Ka, with acetic acid ionizing water, you get following equilibrium established. And this is related to the lab we did this week as well as last week. The Ka is the ionization constant for this. So you have the values, and associated with this, you have the concentration of the H plus, that's from the pH, and then the acetate, and then the acetic acid alone. That's called the acid ionization constant. Since the concentration of water is large and does not change, it's omitted from Ka. So at 0.2, at 25 degrees Celsius, a 0.1 molar solution of acetic acid is 1.34 ionized and has H plus of 1.34 times 10 to the minus 3. Calculate the Ka for it. The two concentrations are equal, so you get the H plus equals the acetate concentrations 1.34 times 10 to the minus 3. The moles per ionized are there. Unionized that. So substitute the concentrations into the equilibrium expression and essentially put those values in there. And you get 1.8 times 10 to the minus 5 there. And in this case, that is the Ka for acetic acid, 1.8 times 10 to the minus 5. This is the Ka for acetic acid. Plugging the values in there related to that. What is the H concentration in a 0.5 molar sodium acetic acid solution? The Ka is 1.8 times 10 to the minus 5. You put the equilibrium thing there. You plug the values in there. Because each molecule yields one H plus and one acetate, the concentrations of the two ions are equal. So you have Y there. So at equilibrium, you have a 0.5 minus Y, and then you can plug the values in there for each value. And so you essentially have Y squared and 0.5 minus Y there. That equals 1 times 10 to the minus 5. Assume Y is small compared to 0.5 there. So it's essentially equal to Y, and then you get Y, solve for Y squared, and you take the square root of both sides there. You get 9 times 10 to the minus 6. Y is 3 times 10 to the minus 3 moles. So in this case, if you use the quadratic equation, you get 2.99. So it shows it's justified. And then essentially you can get the pH here. The pH would be equal to 3 for that molar solution of acetic acid. Calculate the percent ionization in a 0.5 molar acetic acid solution. The ionization of weak acid is given that way. Percent ionized is there. The ionization of acetic acid is given this way. Here, the concentration of H plus divided by the initial percent ionized, and you have 3 times 10 to the minus 3 divided by 0.5 molar, so it's 0.6% ionized. This shows why it's a weak electrolyte. And here's some ionization constants of weak acids. Solubility product constant is the next one. A dynamic state where you have 2 or more opposing processes are taking place at the same time. Chemical equilibrium where the forward rate equals the reverse rate. The solubility is the equilibrium constant of a slightly soluble salt. So silver chloride is equilibrium with its ions in aqueous solution. If you've got something like this, where you reacted the sodium chloride with silver nitrate, you get the solid. So that's the equilibrium constant there. That does not affect it when it's a solid. And so this is getting the next term, KSP, which equals the silver ion concentration solution times the chloride ion. And this is what indicates the solubility of a salt in water. Rearrange there, that's the KSP, and that is a new constant called KSP there, and that the solubility of silver chloride in water is 1.3 times 10 to the minus 5. Because each formula yields one silver ion and one chloride ion, the concentrations are equal. So basically, the KSP has no denominator in this case. And so essentially, you have the KSP is 1.7 times 10 to the minus 10. When the product of the molar concentrations of the ions in solution is greater than KSP, precipitation will come out. If the ion product is less than that, no precipitation occurs. The KSP value for lead sulfate is 1.3 times 10 to the minus 8. Calculate the solubility of lead sulfate in grams per liter. Well, how would you do that? Well, the equilibrium equation for this is here. You set up the thing again like this. This is solid, this is aqueous, and this is aqueous, okay? You have the KSP value equals the concentration of those two there. You have two of the ions are equal, so you let Y equal that, substitute Y into it. Y squared is 1.3 times 10 to the minus 8. Take the square root of that. That gives you the solubility of lead sulfate in grams per liter. And that's kind of what you did with this week's lab, where we had, with the demo, they're showing the barium sulfate come out in the precipitation. Now, the common ion effect, regarding how does that affect equilibrium? If an ion is added to a solution already containing that ion, it's called a common ion. The shift in equilibrium upon addition of an ion already contained is known as the common ion effect. So the equilibrium equation of silver chloride is this. Silver nitrate dissociates in aqueous solution like that. You get there. Silver is common to both reactions. Upon the addition of silver to it, the equilibrium will shift to the left according to the Lachetier's principle. So if you add silver nitrate to it, to that side, it'll push it in that direction. If you were to add salt to it, it'll push it in the other direction too, to the left. Silver nitrate is added to a saturated silver chloride solution until the silver ion is present. What will be the chloride remaining in solution? Use the KSP there. You substitute the values in for each. You get the solvation there. In the absence of silver nitrate, the chlorine is 1.3 times 10 to the minus 5. But look at the new one. That's 1.7 times 10 to the minus 9. So it's very, very small. This is an example of the common ion effect. Solubility constants for KSP. Now, acid-base properties of salts here. Hydrolysis is a term used for the general reaction in which a water molecule is split. Salts that undergo the anion of a weak acid undergo hydrolysis. The net ionic equation for the hydrolysis of sodium acetate is this. So you have the acetate ion plus the water molecule reacts to form acetic acid plus hydroxide. The water molecule splits. The solution is basic in this case. The sodium's not involved there. So if you have a weak acid that contains salts that contain the anion of weak acid undergo hydrolysis. Salts that contain the cation of a weak base undergo hydrolysis. Ammonium chloride there. You have the ammonium ion plus water molecule goes to form that the ammonia in solution plus the hydrogen ion, the water molecule splits, the solution is acidic. So essentially, if you have ammonium chloride, the solution will be acidic. The previous one, if you have sodium acetate, the solution is basic. Salts derived from a strong acid and a strong base do not undergo hydrolysis. And so basically you've got a combination of them. They'll be neutral. And you kind of had saw that with the buffers that we addressed last week. Buffer solutions that control the pH. A buffer solution resists change in pH when diluted or when small amounts of acid or base are added. And that was one of the quiz questions. And some of you only put part of it. It could be acid or base. A weak acid mixed with its conjugate base forms a buffer solution. Sodium acetate, when mixed with sodium with acetic acid, forms a buffer. If a small amount of HCl is added, the acetate will react with the H plus to form the ionized acetic acid. So if you add it to there, you get the aqueous there. If a small amount of base is added, the acetic acid will react with a hydroxide to form water. And so basically when you have a combination of these factors, and this is what you simulated with the lab, where essentially you use the unbuffered solution and compared it to the buffered solution last week. And basically you use drops of HCl in that. But with a buffer solution, the pH doesn't change much at all when you add addition of HCl or sodium hydroxide to it. Like with this one, if you just add plain water, you add just a little bit of HCl to it, you'll get a huge change in pH. You add a little bit of sodium hydroxide, but if you have a buffer solution of them, you add the same amount of each to it, it won't change very much at all. So that indicates the buffer aspect of the change in pH. So that finishes the introduction. Okay, so that sums up the introduction to the subject. So now what I'm going to do is go to the other PowerPoint and then continue where we left off with that. Okay, so now what I'll do is open up the new one and we'll continue. Okay, now let's define the certain acids and bases here, and we'll talk about each of them as we go through here. Share the screen again. Okay, acids and bases here. Here we go. First, we start with an acid. They have sour taste. Vinegar owes taste to acetic acid. Citrus fruits as citric acid. Reacts with certain metals to produce hydrogen gas. Reacts with carbonates and bicarbonates to produce carbon dioxide. Bases have a bitter taste, feel slippery. A Bronsted acid is a proton donor. So the definitions of acid, Bronsted acid, so proton donor there. Acid is a proton donor. or it is when dissolved in water gives H plus. That's the Arrhenius definition of an acid. So this is the Bronsted-Lowry. Okay. A Bronsted base is a proton acceptor. So basically with this, you have ammonia. It accepts a proton from here. One of these protons goes over there. You get that, and it forms hydroxide. So basically, you have the Bronsted base is the other definition of that. You have the base reacting with an acid, which is the water. It gives up a proton. This gives up proton to that. And you end up with the acid on the left and the base on the right too. And basically, this is called the conjugate acid and the conjugate base after the reaction has taken place. So in this case, you have this is the base, the water is the acid there. So acid-base property is water. You break the water molecule down to H plus OH minus. That's called the autoionization of that. Yeah, the reaction of one goes to the other like this. You have the acid and its conjugate base, the base and its conjugate acid on the other side. The ion product of water is the water is constant. So that's the Kw that I discussed earlier. That's the product of the molar concentrations of H and OH at a particular temperature. And at 25 degrees Celsius, that's 1 times 10 to the minus 4. So that's where pH comes from. That's the negative log of the hydrogen ion concentration. If the hydrogen ion concentration is greater than OH, essentially acidic. If the hydrogen ion concentration is less than OH, it's considered basic. What is the concentration of OH ions in a HCl solution? Hydrogen ion concentration is 1.3 molar. You plug the values in there. You can then get it. And now we define what the pH is. The pH is equal to the negative log of the hydrogen ion concentration. If a solution is neutral, that pH is going to be 7. If it's acidic, it's less than 7. If it's basic, it's greater than 7. And then essentially, as the pH goes up, the hydrogen ion concentration goes down. Some pH of various common fluids listed there. A pH meter, and this is what we're going to be using next week. This is also be used to indicators the changes of color. Change in color. You did that before as well. So you have the POH is equal to negative log of that, and so you have the Kw is 1 times 10 to the minus 14. The negative log minus the log of the OH is equal to 14 there. pH plus POH is equal to 14. The pH of rainwater collected in a certain region of the US was 4.82. What is the hydrogen ion concentration in that? pH is a negative log of that. You plug the values in there, get the negative log. The OH concentration of a blood sample is 2.5 times 10 to the minus 7. What is the pH of the blood? So the POH is equal to 6.6. You subtract that from 14 and you get 7.4. Now, strong electrolytes, this is what this week's lab is about with 100% dissociation. Sodium chloride dissociates in water to form sodium ion plus things, plus chloride. Weak electrolyte, it's not completely dissociated, and you have the combination of both of them there. Strong acids are strong electrolytes. They go totally, and then you have a whole variety of different acids there. Weak acids are weak electrolytes, and that's because the equilibrium is more on the left-hand side with these on the left. Strong bases are strong electrolytes. Examples there, you have total dissociation with ethers, and then weak bases are weak electrolytes. And again, that's what this lab is about. The conjugate base of a strong acid has no measurable strength associated with that. H3O plus is the strongest acid that can exist in water. The OH is the strongest base that can exist in water also. So here's some relative strengths of various acids and conjugate bases. And you'll get more out of the reading the textbook to understand the whole sense of conjugate. Strong acids, different examples of those. Weak acids like that. What is the pH of a 2 times 10 to the minus 3 nitric acid solution? You have a strong dissociation. You start at the end. You plug the values in there. In the end, you have 0.02 molar. You plug the values into it like that. You get 2.7. What is the pH of 1.8 times 10 to the minus 2 barium oxide, hydroxide solution? That's a strong base, also 100% dissociation. You can then calculate that the same way, and you get that. The weak acids and acid ionization constants, and again, this is an equilibrium. Acetic acid is one example. Okay, and essentially most is, the equilibrium is on the left-hand side there. And the Ka, this is the equilibrium concentration of this. It's the same thing as KEQ. This is KEQ there. And when you include the HA in there too, you get the Ka. The Ka is the acid ionization constant. So as the Ka goes up, the weak acid strength will go up too. So here's a bunch of different examples of various ionization constants for weak acids and their conjugate bases. What is the pH of a 0.5 molar HF solution? Well, you write out the equation first. You have Ka equals the hydrogen ion times the fluoride, divided by HF, 7.1 times 10 to the minus 4. You have you set up the formula of this with these. And I'd recommend you do a box form for all of these. You're starting off with 0.5 here. You lose some because it dissociates, it changes minus X there. These both go up by X. So the equilibrium concentration is going to be 0.5 minus X and then X and X there. So then you plug these values in there and you get X squared over 0.50 minus X. And because X is very small compared to 0.05, 0.5, you can ignore that. Okay, there you plug the value in there so you can ignore the x, and then you figure out what the x squared is. And so you have x there. You get the pH of that material is 1.72. When can I use the approximation of this? Well, when Ka is a lot less than 1. That's where it works. When X is less than 1, 5% of the value from what is subtracted. Approximation is okay. How about 0.05 there? This approximation doesn't work. So in this case, you have to use a quadratic equation. Quadratic equation. Identify the major species that can affect pH. In most cases, you can ignore the ionization of water, ignore the OH because it's determined by H+. Use ice to express the concentrations in terms of single unknown. Write the Ka in terms of equilibrium concentration, solve for X. If the approximation method is not valid, solve for it exactly. Calculate the concentrations and or the pH of the solution. So let's try a problem. What is the pH of a 0.122 molar monoprotic acid whose Ka is 5.7 times 10 to the minus 4? Okay, so here you have the aqueous solution, the initial change, and again, they got this diagram here. And what I'd recommend you do is you set up a box for this. So set up a box with everything broken down like that so you can organize your thoughts and get it in there. This is called the ice thing. So you have the numbers all associated with that. You then take put it in the correct form there. You have this as X and this is X, so this is X squared. Then you have this value down there. That equals 5.7 times 10 to the minus 4. The Ka is much less than 1. So the approximation works. You plug the values in there and you get the X is 0.0083. But that's a 6.8% difference. It's not okay in this case. So you've got to use, again, the quadratic equation. And here you just plug the values in the quadratic equation using this, and you get X equals 0.0081. So basically you have that, and it's compared to the other value, 0.0083. So the other value was 0.0083. So this not accurate enough. Percent ionization there for a monoprotic acid like this, strong acid, weak base, and base ionization constants. You have Kb associated with those. Kb is the base ionization constant with that. Solve weak, like the weak acids, except sulfur OH instead, and there's some other Kbs associated with that. Ionization constants of acid-base pairs here. You have Kb. That's Kw, so Ka times Kb equals Kw. A weak acid and its conjugate base, if Ka is Kw divided by Kb, Kb is equal to Kw divided by that. Diprotic and triprotic acids may yield more than one hydrogen per molecule. You ionize in stepwise, so they lose one proton at a time. You can get an ionization expression for each ion stage. Consequently, two or more equilibrium constants are used to calculate the concentrations of species. And then you have those set up like this. And so here's a bunch of different examples of ionization constants. Molecular structure here, the stronger the bond between H and X, the weaker the acid. So HF is much, this is a strong acid, and this is a weak, very weak acid. Bond enthalpies for hydrogen halides and acid strengths for them. And as you can see by the bond enthalpies, it takes much less energy to break apart the HI than it did the HF. Molecular structure and oxyacid strengths. The OH becomes more polar and easier to break if Z is very electronegative, and Z is an high oxidation state. So the interactions there between the different things there, and oxyacids that are from the same number have the same oxidation number. So acid strength will essentially increase with increasing electronegativity. So you have stronger acidity going up. And then acid-base things of salts, neutral solutions there. If you have a strong acid and a strong base, strong acid and strong base, these are neutral. This would be for sodium hydroxide and HCl. Okay. Salts derived from a strong base and a weak acid is basic, so sodium acetate here what are their strong base and a weak acid? And that's because you have there, and then essentially the acid solutions, a strong acid and a weak base. You get that king, and so those will be slightly acid. Acid hydrolysis of aluminum, like that. Solutions where they both cation and the anion things, the Kb is greater for the anion than the Ka for the cation, the solution is basic. So here's a good table that kind of indicates these. Arrhenius acid is a substance that produces H plus in water. Bronzite acid, proton donor. Lewis acids, it accepts a pair electron acceptor. So you got electron pair acceptor. A Lewis base electron pair donor. Lewis acids and bases like there. Here's some more examples of Lewis acids and bases. This is the acid because it accepts the electron pair. This is the base because it gives them up. This is the donor. This is the acceptor. Chemistry in action like this. Okay, so this portion is finished. So I've gone over acids and bases now, and I'll continue with the next part. Tomorrow, or the next lecture, applications of aqueous equilibria, which is the next chapter of our book. Okay, any questions, just come see me. And please read the book before you watch these videos. I'm using the fact that I'm asking you to read these first, and then you'll understand them better. Thank you very much. Have a good day.